Here we'll talk about another electrophilic aromatic substitution reaction, or a group of reagents that add a specific group to an aromatic ring. Now, if we start with benzene, I'll again highlight one hydrogen that's going to be substituted by a group. If we add sulfur trioxide, SO3, and H2SO4, which is an acid catalyst, the same catalyst that's used in nitration. The group that's bonded onto the benzene ring that substitutes for one of the hydrogens is SO3H, which is sulfonic acid. This would be benzene sulfonic acid. So if you have sulfur trioxide and H2SO4 as reagents with an aromatic ring, then the sulfonic acid group is bonded to that aromatic ring. These two reagents, the sulfur trioxide and H2SO4, these are usually provided as what's called fuming sulfuric acid. Where the sulfur trioxide is dissolved into the H2SO4, a concentrated H2SO4 solution. And this is the strongest Bronsted acid that's commercially available. So it's extremely strong acid. We follow the same three steps that we've seen in the previous electrophilic aromatic substitution reactions, where we start with generating the electrophile. If we think about the SO3, this has a resonance structure, so I'm drawing that resonance bracket. If we draw a resonance structure that follows the octet rule, we have two negatively charged oxygens and a +2 charge on the sulfur. So that's a pretty electrophilic sulfur already. Sulfur is one of the elements that can hold an expanded octet. So it's in the third row. I'm looking at my periodic table over here. It's in the third row, so it can hold more than 8 electrons in its valence shell. Another possible structure for SO3 is to have 3 double bonds to oxygen. Both are possible resonance structures, but that kind of shows that the oxygen has electron density, the sulfur is lacking electron density. And when you have an acid catalyst present in solution, so the H2SO4 will draw out that structure. So that strong acid is present in solution. One of the oxygens bonded to the sulfur can do a proton transfer, take one of the acidic hydrogens on sulfuric acid, and then we have this as our electrophile. So this is what we will be using as the electrophile in this reaction. Okay, so we've generated the electrophile. Now we generate the carbocation intermediate. And so we will start with our benzene ring. We add the electrophile. The sulfur is electron deficient, and so it will share, or it will be able to create a new bond with pi electrons on the benzene ring, and we can break a double bond to the oxygen. That way oxygen will be neutral. So we've generated the carbocation intermediate. We know there are multiple resonance structures. You should practice drawing out where you can shift around the pi bonds to have different carbons occupy, or different carbons have the positive charge, so that the positive charge is delocalized around the ring. I'll just write a note that this is resonance stabilized in the same way that we've seen before. And then the last step is removing, so step 3 is removing a beta hydrogen. So don't forget there's a hydrogen there, and that's what will be removed by the HSO4-, that conjugate base. So if I draw HSO, actually, let's draw out the structure. This negatively charged oxygen can then create a bond to this beta hydrogen, and then that will reform a pi bond in the ring. So we re-establish aromaticity. And we have the SO3H group bonded to the ring. This is the same thing as what we drew above. So the ring, and then SO3H, which is benzene sulfonic acid. Now, one thing I forgot to do when I was writing out the mechanism is something that makes this mechanism different from the other electrophilic aromatic substitution reactions we've looked at. And that's that every step, so these 3 steps in this mechanism, are actually all reversible. They're in equilibrium. So this one is pretty much an equal left or right side of the reaction. The second step, where we generate the carbocation intermediate, definitely leans left, and that's because the intermediate is a high energy molecule. And then the last step leans right. For the same reason, intermediate is high energy, so it's more favorable to lean towards the right. So this reaction is special in a way, different from the other electrophilic aromatic substitutions, because the whole reaction is reversible. And there is our reversible sulfonation electrophilic aromatic substitution reaction.